All right, howdy folks. In this video for Professor Carbon, what we're going to do is walk through some reactions. And the majority of these reactions are typically covered in the chapter on carboxylic acids, although we may have snuck in a couple of reactions that you should be familiar from prior content. Again, if you're new to Professor Carbon, what I encourage you to do is actually to pause this video and take a few minutes to work through each of the reactions shown here on the screen. The reason for that is it's your best opportunity to learn and for you to find out what you do and do not know so that you can review it on your own later. And so please do take a moment and pause the video right now. All right, if you're coming on back and you'd like access to these PDFs so that you can fill them all out on your own, or if you'd like to see the complete answers later after the video is complete, as a reminder, you can actually access those on our Patreon page. So all the Patreon followers have access to download the PDFs, both blank and filled out. All right, so let's dive into the questions here. The first one is an amide containing starting material. And so let's just circle that amide functional group right there. And the amide is a great functional group, of course, that's common to amino acids and peptides and proteins. And so it's one that we encounter quite a bit. The reagent here is one that's not super duper common to most sophomore organic chemistry books, but it's definitely one that we encounter an awful lot in the chemistry lab. And it's POCl3. And it's a very powerful dehydrating reagent. And what it's going to do with an amide is it's going to generate the corresponding nitrile by dehydrating. So let me just circle, I've got one water there and two H's there. And so what we're going to end up having overall is water is going to leave, and it's actually going to end up reacting with this POCl3, and so we're actually going to make a bunch of HCl, and then we're going to make some POOHs, and so that's how it's going to work. Okay, overall the product is going to be a nitrile, so let me just go ahead and fill that in here on the box. And we like nitriles because they are kind of a dehydrated form of the amide, and sometimes we can reverse that through an acidic hydrolysis. So if you take a nitrile and you partially hydrolyze it, you can get the amide out, and if you really push on it, you can get it to go all the way to the free carboxylic acid. Okay, the part B here that we're moving on to now, this is a very favorite molecule of me, and it's one of my favorites, is acetophenone. It's a very classic ketone, and you'll notice it's at a different oxidation state. So usually we refer to these amides or things like anhydrides as being at the +3 oxidation state. Ketones are at the +2 oxidation state, and so this one definitely does not follow the acids, anhydrides, esters, and amides kind of reactivity. It's a very different functional group, and so it's kind of important to recognize that initially. And so take that as a reminder that not all carbonyls are created the same. The reagent here is HCN, so that's hydrogen cyanide. It's a very toxic gas. And one other thing that it's really good for, though, is adding a single carbon to molecules. And in this particular case, ketones are going to end up making the cyanohydrin. And so this would be the cyanohydrin. And what we've done here is added H to the carbonyl oxygen, and then CN attacks that protonated ketone intermediate. And so that's how you end up with the cyanohydrin. The reason it's thrown in here with acids and esters is because you can take cyanohydrins and hydrolyze them with H3O+ and actually generate the corresponding acid from them. So I'm just going to abbreviate so that it fits in here, OH. And then we might have our methyl group, and then we might have CO2H. And so you can hydrolyze that nitrile carbon, just as I alluded to above, all the way to the free carboxylic acid using H3O. So that's a little bit of a bonus answer, but it lets us extend that ketone by one carbon and make that carbon an acid. And so we'll see that that's a common theme with some of the other questions on the Professor Carbon channel. Okay. This one up above now, this is also kind of a throwback question to what should be a little bit earlier of a chapter. Aluminum trichloride is a very powerful Lewis acid, so I'm just going to label that Lewis acid. We're in benzene, and it turns out that's going to be a very important part of this because anhydrides are really good electrophiles, and they need some nucleophile to attack them. And there isn't a really great nucleophile in aluminum trichloride. Actually, Lewis acids themselves are electrophiles, right? So we take a lone pair and you attack a Lewis acid with it. And so it turns out benzene here is going to have to be the nucleophile. And this is a throwback to the electrophilic aromatic substitution chapters. Ultimately, this is going to undergo a Friedel-Crafts reaction to make acetophenone, which conveniently enough is drawn right here. Now, the way that you get there, remember, is that this will bind your Lewis acid, and then ultimately we're going to go through the really unusual O triple bond plus intermediate, and that's our key intermediate to engage in the electrophilic aromatic substitution. If you'd like to review on electrophilic aromatic substitution, there's a couple of examples on the Professor Carbon channel, and so you can scroll through and find those. And as a reminder, the chapter is up here in the banner, and then the explosion diagram over here tells you what kind of question it is. So you can look for the EAS or aromatic tag, and then you can look for a mechanism over here. All right, so that's a little bit of review on part C in our electrophilic aromatic substitution. This one looks like we have to fill in the starting materials, and often these are a little bit more challenging, and the reason for that is because we kind of have to think backwards. And so we have to identify what SOCl2 does, and so it makes acid chlorides. So that means whatever our starting material is must be an acid of some kind. That way we could make the acid chloride from that acid. And then the second part here is going to be aniline, and so that's going to be our nucleophile to attack the acid chloride. And so if we zoom over to the product that's drawn, we can see our aniline here, and conveniently enough, that's part of an amide functional group at the +3 oxidation state. And so we can imagine breaking that amide backwards and then putting a carboxylic acid there instead of the NHPH. And so the answer I would provide for this question would be this. Now, funny thing for those of you that want to go through and rename these all as being R and S, if we look at this, the highest priority group on the stereocenter should be oxygen, so that should be 1. And then the next highest priority, let me see here, so phenyl ring is carbon containing, this is carbon containing, but this one is oxygen, so that should be 2. And so that should be good, and then 3. And so we can go through and do that full assignment for our stereocenters. And then let's see here, so this should be the S stereochemistry. Kind of fun there. All right, the final question has to do with adding 1 carbon to this molecule. So we have our nice cyclopentane backbone here. We have a nice cyclopentane, but we have to replace this bromine with a carbon. And there's actually going to be 2 viable ways to do this. The first one that many of you probably are thinking of would be to use magnesium 0. And so that would make the Grignard reagent. And then we can go to here with carbon dioxide. And carbon dioxide, then H+. And what that does then is the Grignard will attack the central carbon on carbon dioxide. It'll make O-, and then that O- will end up being protonated with H+, and so we'll get the free carboxylic acid. So that would be one way to do it. Now, experimentally, it probably wouldn't be the first thing I would recommend to a student to try if they actually had to do this in the lab. And it's because I think that there might be a slightly easier way to do it. And the reason I say slightly easier is not because these are inherently challenging reactions, but it turns out getting really dry CO2 into your reaction is slightly difficult if you're using things like dry ice or if you're trying to produce CO2 on site. Of course, if you have a nice dry gas cylinder, you can, of course, plumb that in, and that helps out a lot better. But also making Grignard reagents is very water sensitive. So for those of you that are taking an organic chemistry lab course and you're actually making a Grignard reagent in that lab course, often you have to go through the trouble of, drying your glassware and grinding the magnesium up. And so sometimes the yields for that are not the best. Sometimes they're great, but often it can be quite problematic. A different way to do this would be, and I'm just going to change colors here to make it a little bit easier. What if we used NaCN, or sodium cyanide, and borrowed the trick I discussed up top here, where we extend this chain by one carbon and then hydrolyze the nitrile. And so if we use sodium cyanide, we might be able to make this nitrile, and then we could hydrolyze this with HCl or H2SO4, really any good H+ source, as long as that there's water around to do the hydrolysis reaction. And that hydrolysis should work out quite nicely. Now, some of you might be recognizing that this is a secondary carbon, and often doing an SN2 reaction on a secondary carbon can be complicated. And what I would say here is that it's a relatively unhindered secondary carbon in this case, so there's not a lot of branching or spinach dangling out next to it. And the nice thing about the cyanide anion is it's not particularly basic, but because it has this really nice linear geometry, it turns out to be quite nucleophilic. And so strongly nucleophilic and not very basic will tend to favor the SN2 pathway over the E2 pathway. And so I bet you can get this SN2 reaction to work even though it is a secondary carbon. All right, so that sums up these 5 reactions. Again, if you're enjoying these videos and hopefully you're sharing them with your friends, please do leave us a comment in the comment section for Professor Carbon on the YouTube channel. Please do become a subscriber. It's very important to us to see the number of subscribers creep up. That helps us know that these videos are helping people learn organic chemistry, and it provides some encouragement to continue to make future videos. Lastly, if you want access to these questions in PDF format, you can go ahead and follow us on the Patreon page. And if you do that, you can access them both in the blank form and the filled out copy. All right, so hopefully you'll view the next video.